Hey everyone, how's it going? How are we all doing? Welcome to another stream. So, last stream we did a test to see if we could optimize our BVH traversal by doing something a little bit different. And turns out it wasn't good, and I can explain why. So, if we give it a run, see, it works fine. Like, this is rendering using the new sort of ray tracing, but it's dead slow. So it went to a mess now. We made it like more than 2 times slower, and we're getting to exactly why. Hey Ramil, hey, thank you, thank you, sir. So effectively we dispatch across the whole screen, right? Each thread gets a pixel traditionally. But I was thinking, you know what? Like, so inside the compute shader for that sphere ray tracer, this one, it launches 8x4. 8x4 meaning like, well, okay, meaning there's 32 threads, right? And because the hardware that we are running on, it supports natively 32 threads that can run in lockstep. So each wave is 8x4, right? So the thought was, 8x4 threads, when you have like a sphere or whatever, going over these 8x4 threads, you can kind of get less wastage if you could probably have 2 threads process a single pixel. And we had another thing which could sort of back up this. So instead it'd be a 4x4, right? So instead of doing an 8x4, we can make it a 4x4 and have 2 threads process a single pixel. And we had thoughts, right? We're processing this BVH, and we could process 2 nodes at once. Because it's just a binary tree, so we can have 2 nodes being processed by 2 different threads for the same pixel, right? And we'll 2 spheres at the bottom, so it's 2 spheres for 2 different pixels. Sorry, for the same pixel. But turns out it's actually slower, because one, it's got to run twice as many waves, right, to actually cover the same amount of pixels. But yeah, the reason why is like, if you have a sphere which goes over the pixels, you ideally will get less, like, yeah, maybe this is a case where our solution is very bad, I guess. On the 8x4, you'd get like, I don't know, 40% occupancy, whereas on the other one, you'll get, basically about 70% occupancy, and then this one you'll get like basically nothing. So that's where a problem could lie. But also, I think where you get the biggest wins is when the things are so small, right? When you have stuff that covers the whole screen and it's huge. Like 4x4 pixels is tiny, and the divergence that goes across the pixels isn't going to be as bad as you can sort of draw it here in a very small, right? So I think those are the main issues with it. But it's good to try out though, and I've learned stuff from it. But what we're going to do is we're going to sort of undo this change in a way. Like we've still improved the code, so I'm going to just, rather than reverting it, I'll just make the changes to make it 1 pixel per thread, 1 thread per pixel instead. And then we're going to investigate why this BVH is actually not as good as it could be. You can see here, your left and right child, and one is inside the sibling. So there's something weird with the generation going on, causing that to happen. So it's not as optimal as it could be. So investigate that as well. So let's just quickly undo. So sphere, ray tracer. So this one here. I was going to keep it around, but I'm thinking it's probably not going to ever be good. I'd have to maintain it as well, like 2 versions. So let's remove 2 times across the width. So it's times it by 2 because of that reason. Let's divide by 2 here as well. Good. Hey Russ Musco, how's it going? How do you decide what goes in each side of the tree? So we've got a bottom-up algorithm. We kind of followed this blog here. But essentially I can just describe it. We have I've taken some things from that blog. I've not taken everything from it. So essentially we have our spheres. You can imagine them in an array, right? And we're just saying, so we can basically tell, like, there's 2 spheres per node, and you can tell based on how many leaf nodes you have in a binary tree, how many overall nodes you have, right? Because it's number of leaf nodes take away 1, which means the total number of nodes that you need in a tree for this many is so it's the number of leaf nodes times 2 take 1, and that gets you the number of nodes in total. So basically for 7 or 8 spheres, it's 7 nodes, right? So effectively what we do is we launch a compute shader that goes over all of the leaf nodes, and they know what spheres they're going to wrap a box around, and they wrap a box around their spheres, right? And then they just go up. Like this one tries to go up, and since this was the first one to reach this node, it's going to terminate itself. And then this one goes up, and it's reached it the second time, which means it knows that this data is accessible, so it can then look at the sibling data, read it, calculate the new bounding box, and then we just repeat that algorithm all the way up to the top. So there's some atomics involved and stuff like that. I don't know which spheres to pick. Well, this is leaf node index 0, this is leaf node index 1, right? So it's simply just 1 times 2, and that gives me my start 1 in the array, basically, right? Yeah, so it's just that simple. But if you're interested in, we do have the VODs up on YouTube. So we did actually create, if you want to see me actually programming it, is all up on there. Oh yeah, I forgot about a key thing. We use on the CPU right now, they're sorted in Morton curve order. The blog goes over it. We do this. So we basically sort them via their Morton curve. So we take a 3D coordinate and we turn it into a 1D coordinate, which means that everything that's sort of next to each other in 3D space will be sort of next to each other in like a 1D space. And it repeats in this Z. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? And it repeats in a Z at the micro level and at the macro level and at the more macro level, you know what I mean? As it just layers up across 3D. So we use this from that blog that I linked. So yeah, we sort these spheres by that, and then that way they should be next to each other. But something feels a bit off, so we should reinvestigate what that is, right? But yeah, that's about it. So I think we need another for loop. You know, always need another for loop. Plus 2 BVH nodes count. Yeah, so we're just going over the 2 BVH nodes now. Right. So we want to. What do we want? Is hit. We want like a left and right is hit, right? Okay. So we're traversing down. If we hit the bounding box, then and it's a leaf node, we'll check the spheres. So is hit needs to be. Uh, 2. Next, BVH node index. Okay, so we just need to add that to here. Hey LCT. That explains the long distances, maybe. It depends. Yeah, they are sorted first though. But I don't know. They should be close to each other. But we have to analyze it, we'll do some debug stuff. Get to see it visually. But yeah, how's it going, LCT? What have you been up to? Good to see you. So yeah, also last stream, we've started putting these max iterations on so we don't get these GPU crashes. And we're going to we're going to basically bounds check. Well, sorry, we're going to bounds clamp, right? So we don't go out of bounds and, you know, crash the GPU. Not so red, how's it going? Yeah man, doing good, doing good. How you doing? You had a good week? There would be long edges in space. In any space filling curve. Yeah, but the bit that's kind of strange about it, and I can't show it now, is that the higher levels are. Yeah, I need to think. Yeah, maybe I need to. I'm doing the simplest thing. I need to sort of see. Because they sort of, I think they might solve this problem the way they basically do a binary search and try and probably fix this up. But I kind of skipped this part. Yeah, I think they did like a binary search somewhere to solve the problem. But yeah, I need to look into it. Awesome, good to hear. Good to hear. Yeah, I'm not doing bad, just yeah. I'm doing okay. Been quite tired the past couple of days and oh, had a couple of long days. But things are going good. I found out that from the 11th of December, right, obviously, I'm off work all the way until the 2nd when I go back. So I've got like 3 weeks off. So in less than 3 weeks, I got 3 weeks off. Which is super nice. I get to relax, spend time with the family, and yeah, it's gonna be good. Right, I think we need to initialize those to 0. We should do that like this in C. Isn't that amazing? Okay. So what else do we need to change? So we just need to put that in a loop, right? Team element gets set twice, that's fine. Right. So now we can move all this sort of wave stuff because we're not sharing stuff between 2 threads. I'm doing something silly and dumb. Right, let's just give these good names. Right team in, that's just team in mat, team in element. Right, hit left is hit 0. Is hit 1, is hit 1. Right. Okay, that is fine. Yeah. Yeah, so we also found out last stream, if we enabled this, which feels like an optimization, which allows us to early out traversing back up the tree. Well, yeah. So we basically do two checks at the same time, right? We check the left and we check the right hand side. If we hit the left and the right, we back up the right onto a little stack somewhere, and we continue traversing down the left hand side and check the 2 and repeat. And then if we basically don't hit anything, or we finish traversing everything, we'll just be able to jump right back to where that thing is in the array. But before that jump back, we can check to see if we've hit anything closer, and if we have, just don't bother checking it and go past it. But we found out that it probably uses a lot of VGPR space, so enabling it actually makes it slower. But that's for our very simple scene. We'll have to see what it's like later on, so I'm going to leave that commented out. Right, so we should be able to get rid of all this crap. It was had to do because of that sharing. And that should be it. Man, I'm really enjoying this mechanical keyboard now. I completely forgot how awesome it was. Man. Any progress on the BVH stuff? His performance looking good? No, it turns out that thing we was trying out was a terrible idea, so we're just reverting it now. Effectively, having 2 threads per pixel is not a good idea. If the objects are very, very small, it might have been a good idea, because there would have been a lot of divergent threads within the same wave, possibly. But I think just because the amount we're going through so many big BVH nodes or whatever, we spend a lot more time doing that, so it's probably going to be quite similar across the 8x4 pixel range. That actually wasn't a good idea. It actually was twice as slow, rather than being yeah. So we just hopefully undone it, and yeah, we got this for loop in here as well. I want to see if I can make that a variable that's passed in, because the compiler might unroll this, and yeah, that won't be good, or it might not be good. I want to compare it. Hi there, Mr. Ket Payne. How's it going? Welcome back. Good to see you. Yeah, man, not doing bad. Not doing bad. Just came across this article. It's a different approach though. Nice. Different is always good. Good thing to read. Hey there, Shiloh. How's it going? Or Shiloh. How's it going? While the Z-order curve by more precise significant step in parallel BVH construction, the stochastic subsets method builds upon and enhances this method approach by focusing on optimizing the construction of the most impactful parts of the hierarchy and improving the parallelism performance on the GPUs. I'm not sure what that was saying. No, I haven't got loop unrolling. Basically, because SpearV is a compiler IR, like the GP drivers just basically turn it into LLVM, and then LLVM just does all of its optimizations on it in the driver. For the most, basically all drivers do that. So to force it not to unroll, because they're going to inline and unroll everything usually, you basically just give it something it can't unroll, and then it will just like you give it a variable from the CPU, and then it's like, what is this? So it has to do a for loop. In other words, stochastic, because uni, fair play. Yeah, so basically SpearV does all the optimization. I just output ugly, the first level of the IR, where so it's easy to generate, and then you're meant to go over and optimize it later. I don't do that. I was gonna do it for fun, but I just wanted to use the compiler more. Right, this seems like it needs some offline reading to really understand it. But yeah, why is this horizontally fat? Like what's going on with this viewport? I want the vertical fatness, What is? But yeah, I really got to see what this is saying. Thank you though. I'll leave it open. This is where like in like the next stream we're like, right, we're changing everything. Stochastic. Anyway, subset BVH construction. Right. Hey there, Sully. How's it going? Might give SPIVy a try in the future. I didn't touch the compiler for the last 2 weeks. Awesome. Yeah, so the thing about SPIVy is actually very restricting. So you're not going to be able to do all the crazy cool stuff you can do on CPU. So you can't have pointers, you can't have, well, you can have pointers, but they're logical pointers. So you kind of have to know where the pointer actually is coming from. Oh, sorry, what the pointer is pointing to at compile time. In a way. Yeah. So, yeah, it's very restricting, but it's definitely like, if you're going to do some GPU programming and you got a language, like compiling that to SPIR-V is just a no-brainer in my opinion. But apparently 99% of the world doesn't agree with me because we don't have it right now. But anyway, I'll just sit here, hear it, and enjoy it. What compiler are you talking about? So see here, this is C, right? Programming in C, and it's shaders. Basically, I spent like a year and 3 months making a C compiler that, from scratch, custom preprocessor, custom, everything. And it just basically compiles C into SPIR-V. So you can use C for shaders, so you can share structures, functions, and get the same semantics across your CPU and GPU code. But you obviously have limitations, basically. But it's good. It's good. Because, yeah. Right, so I'm pretty confident in just running this thing because we've bounds checked everything. Wait a minute. Oh yeah, we have. Oh, we haven't. Right, let's give this a run. Right, we're back. So that's twice as fast already. 1.1 ms. I suppose that's a 0.8. Should we feed it a constant of 2 or something? Or there's a way to maybe do that. No, there isn't. Right, let's see if there's any better. Right, so that for loop. Right, it's not really made it any better. Might have made it a bit worse, I'm not sure. At 1.2. So maybe the unrolling, if it is unrolling, is better. No, it's actually the same. It's probably not unrolling it. Okay. Right. So what are we going to investigate now? So let's make this more flat. Yeah, so we've got this highlighting stuff where we can sort of highlight, see the nodes, right? But what would be great is if we can like just see the contents of those nodes. So I'm wondering if there's an easy way to do that. So now we're rendering using this BVH. We should be able to hopefully do that. It might be, you might have to introduce some slower code though. But effectively you want to say, when you enter here and you get into this sphere, you probably want to check if any of those debug visualizers are on. Then you want to say traverse up the tree and see if your parent is one of these, basically. If you or your parent is one of them. So yeah, you're gonna say if BC debug level, if that's not equal to 0, we'll basically say while, so you'll say like node, just call it node, be right. So BVH node index, you're gonna say while node, right, because 0 would be the root. Yeah, I don't want to deal with it now, but if I have the backend working, I might have to BV as well. Sweet. That was not correctly. Seeker gets compiled to GLSL. No. SpearV. So GLSL gets compiled to SpearV if you use it for Vulkan as well. This guy. So it's literally just like a compiler IR. It's like LLVM IR, but for shaders. And basically, if you use the Vulkan API, it takes it in. That's what it takes in, the shaders. But yeah. So you say node equal BVH. Parent, right. So what we're trying to do is you need to find the level. Depth, that's it. Right, so if this is equal to the depth, so what you want to say is like hit.success, right, is equal to, there's a did hit as well. Right, why is there a did hit and a success? What's the difference again? Oh, because it might not have been within an acceptable range. Got it. So we'll just say success equals false and did hit equal true. Something like that. It's just debug code anyway. And we're just going to traverse up, and if we land a hit on the on a sphere which is, yeah, but do you want us to do the level? If you're visualizing the levels, you're going to visualize all spheres anyway. Yeah, this is not good. You only want it for the other one, the node. Okay, so you go up until you hit until you say node is equal to this node index. And if we find that, we break, and then we make success true. Same, we just hit it. Yeah, so you want to say if success. So if we're debugging and we actually hit, see if we can keep the hit, basically. And then we break, and voila. So that should keep going up, and then you'll hit the parent eventually, and boom. Okay. So we should be able to, excellent. We've seen a lot of anti-aliasing dust. Isn't that wonderful? So this is all the anti-aliasing being drawn without the actual spheres. My favorite anti-aliasing dust. Right, so I thought we did a thing where we said oh wait. Right, how do I get rid of my anti-aliasing dust? You kind of want to go into here regardless, right? Yeah, and then do another if statement. But this after you do this. Wait, the hit. To get rid of the AA dust. Oh yeah. Oh. Rightio. Okay, so now I can debug visualize everything. Huh. I don't know if that one should actually exist. So we should also see what we're So it's probably best if we start off flat, right? So let's just get rid of the sort of wobble, right? Because we have this lovely like animation that goes on. Wait, what? Oh yeah. So if I comment that out, we'll see a lovely animation, right? It's all cool and everything, but we want to like it just gets in the way. So, or maybe it does. Actually, maybe it's fine. Maybe it's what we want. Because we can see how the box reacts to the, I don't know. See, I wonder if we should just do 4 spheres anyway next to each other. Use 4 spheres as children. Because you're going to get a lot of this anyway. We might be better off doing 8. Maybe not 8, actually. Because you'll get something like that in a box. You have to check all 8 of them. Maybe 4, though. Right, that just went back. The parents went back there. Pretty much. And it went wider, okay. Okay, it's looking kind of okay. That's a bit of a... Right. So the problem I'm sort of facing is I want to analyze is this parent this is basically the most root level. Right. We ignore the root node. We just check the first level with 2 nodes, right? Because the root node is just 1, right? So this is this one and 2. Like, which one is it? Yeah, this one is inside this one. That's not good, is it? Like these two, like like ideally we want it to be split in half, and we want to investigate why that is not happening. Um, why aren't I seeing any box? Oh, right, it's this level thing. Yeah, so it's literally like this backside here. So what we should probably do, because this is a more wider shape than it is um, tall or like tall or yeah or deep. Um, yeah, so I think what's happening is it's probably doing it on the Z or something like this. Yeah, we should. So if you go to the most sort of go to the right hand side, the most left most of that, obviously down there. Then the most rightmost. Right. That's at the back on the left. And these two are like not even next to each other, but I guess. Oh, that's not good, is it? Of all the ones that should have been next to each other, you would not expect that, right? But I guess looking at it. Huh. Um, so is there anything we do with the colouring? Yeah. Right, so let's read into that blog a bit. That we're kind of been inspired by. There was a line here. Um, where is it? It's just the fine split code or something. Yeah, so we sort by the Morton curve. Um, but I think it uses the. It looks for the most. Like the furthest long bit with a match or something like that, and it's sort of. So maybe we can sort the array. Yeah, so it does like a binary search or something like this. It's very. Yeah, this part here. You got all these things as the space filling curve has some long edges. Right, so you mean because of this? Do you mean this is a long edge, right? Okay, gotcha now. Right, so you can never get Right. Okay, good to understand. So there is that other one that people were using. What was the other space filling curve that is harder to calculate? But that might not be a problem if we kind of do it. Um, what was that other one? Hilbert curve. This one. This one doesn't have a long edge, from what I remember. So it does. Right, from the fact you might not fill the whole space. Damn it. All of them do. But is it... Okay, let's look at a pattern and see if I can find it, because I don't think... Oh my days. It's not easy with the graph paper there, is it? So it's going along like that, right? So if you don't have a sphere there, then I guess you get a bit of a gap. Like, yeah, you might have a sphere there. Oh my days. You might have a sphere here. Okay, I get it, I get it, I get it. You might have a sphere here and here, and you're like, they're next to each other. But then what happens is it's actually, this will get bundled with one over there or something like that. And this will just get bundled with a different one. Right. Okay, I see how there's... Right, zigzag, and then there's this... Or sweep, then there's zigzag. But they don't have them in the top of the tree. Um... Hmm. Not sure you mean by that, exactly. But yeah, they do this thing. They say they do this thing here where um, it is right. We start with the range that covers all objects. The appropriate position to split. Yeah, so defines why. So where to split. Um, so the index of where to split. That's what y means in this. To the highest bit that differs between the Morton codes within the given range. In other words, we aim to partition the object so that the highest differing bit will be 0 for all objects in child A and B. The intuitive reason that is a good idea is partitioning objects by the highest differing bit in Morton codes corresponds to classifying them on either side of an axis aligned plane in 3D. In practice, it's the most efficient way to find right. So I'm not quite sure exactly. So this just tells about how to implement it. I'm not sure exactly what that means given a Z curve, but yes, I think it's picking. I think it's able to pick to solve that problem basically, where that sort of long edge. Where the bounds are always big, right? They did any top-down things. I'm not sure you mean by top down. Yeah, we basically just have a big tree and we go top down. Yeah, we traverse top down. Transition the high bits are what you call long edges. Okay. Hmm. So would you think this fixes the problem? Yeah, we're not doing top down, we're doing bottom up generation. Yeah, this talks about top down hierarchy generation. But yeah, but we do the bottom up version. It's like this. It's not the same though. It's inspired by it. But yeah. I wonder if switching to Hilbert space would minimize. I don't know if it will actually. If it would minimize the. Or maybe if we could. See, this is doing a binary search. So find where to split. I wonder if we could do a sorting. To sort, but maybe not. Like you do another sort that goes over the array and maybe tries to sort of minimize the amount of but you can't probably. Hmm. Wait, we should make another button maybe. These are a little bit too big. Oh, that's fine. Hmm. Yeah, this one is like the perfect specimen. You know, it's just got like two there. Um. Hmm. Yeah, so that's probably. Yeah, I think we should give that Hilbert space a go and see if it just ends up being better. Um. If not, we should probably take a look into the model and be like, say, if it's wider, maybe do the Z curve differently. So I think our Z curve does the Z axis first, or something like that. Maybe rotate it around the other way. We'll give that a go. You can move the long edges by swizzling the coordinates. Yeah, see, that's what I was thinking. Just with one of those two things, right? Is basically just rotating it the other way around, depending on the shape. Also, yeah, depending on the shape. If it's wider, then we'll probably want to. I think it is Z first or something like that. So where is it? It's here, right? What P? So we can just swizzle it, right? So I think Z is the one in. Different random seed. It is, isn't it? Yeah, maybe that's fine. What? That's not what I wanted. So we need a different P. We need a P and a M. That's not changed it. Swap the Z go there and the Y go there. Yeah, it's changing it, but I think it's not changing it enough. Unless you're able to dynamically with different ordering for each level of the tree. Interesting. Yeah, how would you... Yeah, because essentially this is like an octree in a way. The Z curve, you think of it as like an octree. Yeah, it's a quad tree, right? But obviously, if you don't have anything there, then it's an empty slot. And when you say the next, say we say 4 of them, it'll pick like these guys all together, right? So when you have holes, it sort of skips. Yeah, I wonder if there's a way to analyze the data and sort of sort it again differently after this sort. Yeah. Yeah, because you can't really do anything with the 1D index you get back because you're just dealing with like, you know. You might enjoy plenty, huh? Awesome. Thank you, Surfcat. Appreciate it. Yeah, I think I've been suggested plenty by a few folks, but yeah, I should give them a go. Thank you. Appreciate it. I have heard a few of the things, they're not bad. You look at the bit pattern of the model code. That's true. Yeah, I've sort of seen the way they do it. Yeah, I probably should investigate that. That's a good point. Let's see if we quickly just swizzle it and get anything which sort of is better. To the high level, it's not changing it much. Yeah, still sort of just doing those two sides still. And see how big the bit is for the biggest bit transition in each level of the tree. Right. Yeah, so I think that's what that article was doing, right? When it's doing this, maybe. Right, this actually learn about Morton code and figure out, because I was reading this and I was like, this makes sense, but then I just sort of forgot it. So, so in research sparse octrees often use Morton code. Morton ordering is to mapping an n-dimensional space into a linear list of numbers. So it's like 2D or 3D down to a 1D mapping. If you apply it to coordinates, the Morton order defines a space-filling curve, which is Z-shaped. That is why the Morton curve is often called a Z-order or a Z-curve as well. The curve has some nice locality properties. Coordinates are close to each other in the n-dimensional space. Have Morton curves which also are close to each other too. Right, because there's layers of Z curves. There's a micro and then a sort of more macro Z curve as well. Yeah, whatever. I don't know. So the Z curve inspired a lot of people to do great stuff with compression and data and parallel data construction. Blah 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 blah. If you want to convert a large set of integers into Morton code, you convert the decimal values to binary and interleave the bits of each coordinate. Hey, that's Phil. I finally got my flow code to work. Now I can even trigger events from Flutter code, client-side decorations drawn on the Flow app. Awesome. Cool stuff. So the Z's are blue, greens are Y, and X are red, right? So the X goes, yeah, so they're like swizzled, right? Runs on your composite, awesome. The ultimate flex. That stuff. So, are you using like that Dart programming? Is it called Dart? Are you using the Dart programming language at all to do any of it? Because I know you're not. I haven't seen you mention it at all. So, if your X is the reds, right? So okay, so you've got like right. So that's obviously 5, 9, and then 1. Right. It's pretty clever, right? So it's taking like the first bit of each. Yeah, the first bit of each and make, of each dimension, putting it there. Then the next bit of each dimension, then the next bit of each dimension. Right. Sorry, not dimension. Yeah, sorry, yeah, that's right. Yeah. Yeah. So X, Y, Z, X, Y, Z, X, Y, Z, right? It's pretty simple. So when I was taking the high bit, right? So that high bit would mean the Y. That one's like the furthest away or whatever or something. Yeah. So if this is different from another one, if that is different from another one, then they're probably going to be in a completely different place, maybe. So when they're building the tree, right? Um, but yeah. Also, another thing as well is we're building like a BVH, right? So it's just a binary tree. There's a left and right, and you parent. Um, so if we go all the way left, that should be at the zeros. This is 0 and 1 in the array. Then if we go all the way right, did we go all the way right there? Nah, that can't be right. Huh. They're kind of next to each other. Like, surely these guys, something's up. Like, all the way left in the tree and all the way right in the tree should be on the complete other ends of. Sorry, 2 seconds. 2 seconds. Hey everyone, welcome back. Sorry about that. The embedder. Right, let's get back to this. Oh, either Flutter code, front end, code uses Dart, but my embedder is written in C++, and the compositor is written in C. Also considering rewriting the embedder in C. Fair play. There's a lot of different languages there, but then C and C++ are kind of similar, like toolchain and stuff. Right, gotcha. They might be right next to each other, or they might be. If the bit is differing. Right, okay, so we get back to this. So it's oh, sorry, yeah. No, we won't. We was talking about the yeah, I know what you're saying. Yeah, so I was saying if you go all the way down to the left side of the tree, and if you go all the way down to the right side of the tree, for some reason. Okay, get it back. They're kind of like right next to each other. In space. Why is that? Like they're sorted according to like the Z curve, right? What you're saying is they might be right next to each other. So that means obviously one of them has like a high bit on, right? Or these guys over here have like a higher bit on, but they might be in terms of this. So they might have a high. Right. I still don't get it. Using layers of Z. Right, let's just draw it out. That's some space. You're doing layers of Z. Let's do it this way. Z, 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 Z. Okay. So let's call this one, this one's connected like that, right? This one will be 0. This one will be, there's 4 in each, right? So this one will be 16, right? Or 15, whatever, index 15. So, and then you'll do another Z. So you do another Z, 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 and another Z, 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 Z. Right, so these ones are connected like that. These ones are connected like that, and like that, and like that. Right. So right. But if you can have another layer on top, right? Like this. Imagine this is a 2D slice, right? Or in 3D, you could be doing that, and then you basically have another layer on top, right? And then you'll start again over here. So the differing bit could just be like the y coordinate or whatever, and put it up one. Fair play. So let's start way back up there, but on another layer. Yes. But on another layer of Z. No, I wouldn't do it there. Will it? It'll do it'll do a 2D block. It would do Z, Z, and then it'll go up there and do another layer of Z. And then after that, it will go next door or something like that. Yeah, just something like that. Yeah, so there's one of that and then up there. Okay. Um, hmm. So we're trying to find out why the one on our, like, because this is the start and this is the end, right? They should they? Should they be next to each other? Maybe we should try and replicate in 2D. Like, yeah, the grid might be perfectly sphere over spheres. That's right. That's correct. That is correct. Yeah. So you're not getting each sphere on here. You'd just be getting like one of those spheres, right? Another true point. Right. Okay. I see a problem. Okay. We're not. We're sine curving some animate. We're doing some sine curve animation, right? Okay. That's not going into the Z curve ordering thing. Maybe that's not a problem. But anyway, let's completely get rid of it and see it flat. Um, hey, this Seagull Rush. How's it going? Welcome, welcome, welcome. Draw lines between them, adjacent Z curve. Yeah, I was trying to see if there's a good way to visualize it. Shoot, well, how's this? Crap. Right. Can never be too careful, eh? What did I do to mess that up? That's so dumb. The compute shader probably ran on too long or accessed out of bounds. Probably accessed out of bounds, to be honest. Let's play that music suggestion, Plenty. Is it Plenty? It is Plenty. It's album on. Welcome back, everybody. Welcome back. Right. So I literally just changed position. Oh. It was outside of the screen or something dumb like that. Yeah, yeah, yeah. I don't know what the problem was, but oh no, it was right next to the camera, wasn't it? Because we added 100. That's the reason why. Damn it. Yeah, yeah, yeah. So we had it was on the camera and it crashed the GPU. That's still a problem, by the way. For some reason, I don't know what it is. I need to fix that. Anyway. Alright, we're back. So now we can analyze it again. Yeah, so yeah, we're still getting similar sort of things. They are kind of close, which is very weird. So let's try and figure out why. Yeah, so you're trying to say, can you draw a line to do the Z? Can you draw a line between adjacent spheres after ordering them? I don't have any ways of drawing lines, unfortunately, yet. Probably something we need. You know, just drawing in vectors and stuff like that, isn't it? It's good for that. But yeah, so ideally, if they're right. But surely, if they're in a different, how can they be next to each other in space? And the number be so different? Like, I get how it could do. Yeah, it's just the big Z order. Yeah, I think I get the idea. Get Milton back out. Yeah, it's because you basically have like layers of Z where it just gets bigger and bigger and bigger, right? Imagine if it just filled Zs, a bunch of Zs in a 4x4 there and Zs in a 4x4 there. Essentially, I guess there's the big jump there, where you do get these big jumps. No, but how they right next to each other, the one's right at the start is right next to the one over here. It just still doesn't make any sense to me. Let's dump. So that's the quickest way I think we can figure it out. We're just going to dump out CPU side and just analyze it that way. Just dump all the data out. There's a queue sort here. We've got sort keys. And we go over all the sort keys and stuff like that. So what goes in the sort keys again with the Z curve? Yeah, so it's in the high bits. But that's just also the index, isn't it? Yeah. Something like that. Right. So we want to print out, like, first of all, the sort of the Morton code, I guess. Do you want to print out as hexadecimal or maybe hex? Well, it depends. It'll be a normalized space. We calculate. We have it in normalized space, and we go up to. We have this sort of 1024 resolution. Wait a minute. Did that multiply? Yeah, we multiplied it by 1024. What's the resolution? 20. Oh, that feels wrong. What's going on here? What, are we doing everything right? Times by resolution. Print the X, Y, Z chords. Yeah, I'm trying to think though which ones we want, because we gotta be careful what this is doing. Right, so this is gonna clamp it between. Yeah, because you can fit 1024 in each axis. Basically, it's 30 bits, right? So 10 bits each gets 1024. So okay. So what are we doing? So we've got a normalized from 0 to 1, right? Position, and then we're timesing it by 20 because that's our resolution. So by resolution, what do we mean? So we've got step size of yeah, I think this is a little bit off here, thinking about it. So we're basically doing it from in signed norm space, right? And we're stepping. Wait, that's right, isn't it? You want to step. That'd make you step twice as much, wouldn't it? Let's just double check that. Yeah, that'd make you step. Sorry. What? 1 divided by 20, 0.05. 2 divided by 20. Yeah, so it makes you step twice as much. That's fine. That's what we want because we're in signed norm space. Right, and then we convert that into normalized space. Then we times it by 20. So each sphere how come you're doing a volumetric sweep? Do you? Oh yeah, we're sweeping over the volume. Yeah, because this is how we draw our shape. Basically, we just sweep over the 3D volume, and we just see if we're inside of this sign distance field. And if we are, we plot a sphere in there. Right, that's how we assemble our model at the moment. Yeah, I should probably explain that. Print the normalized coordinates so you can see the range of them. Yeah. I have to denormalize it. Oh, I have to normalize it again, sorry. Yeah. Just figure this one out quick. So the radius is half the step. Okay, the radius is half our step. So we do our position multiplied by the resolution. So I don't know, this feels like they're all sitting on top of each other to me. Like just thinking about it. Because wait a minute. Norm towards scale, what is this doing? Yeah, this feels inconsistent with each other. This is timesing it by 100, whereas this is just timesing it by 20. What was I thinking with this? Because we're timesing it by 20, you've got ones which are next to each other by a difference of like this step size. So, yes, every one of those, yeah, that'll get you probably a difference of 1. Yeah, I think this works fine. That's sphere radius. Times by 100, so everything is just being times by 100. So it's fine. It's consistent. But the way we do this, yeah. Just working on a different scale is all. So it's just more scaled up in the world than it is in the Morton space. So this is doing 1 sphere per grid unit essentially. Right, so I don't ever want it in normalized space though. I want it in that sort of, I want it to go back to normalized space and times it by that resolution again. Yeah, we shouldn't probably print it out here. It's probably not good. What the living what? Okay. Right. So we start printing out this stuff. We want this sort of Morton point. So this is be a good one to print out. So what do we want to know? So for a given sphere, we want to print out probably its index. Then you probably want to print out, and let's just pad that to 3 or something. Yeah, problem is it's not sorted yet in this, which is a shame. It's not sorted yet here. But yeah, we want to see it sorted, isn't it? We want to see it post-sort, don't we? It's probably better. Morton index goes in there, yeah? So you want your 0x... Sorry. Wait. 0x%x. Alphabetically if you print this. Yeah, but then I have to sort. Oh, you mean take the data out and sort it? Right, I see. All right, don't worry. So we want to basically get. I want to know this sort of Morton point again. So let's just get this in here. Right, we'll scale it back to some sort of snorm position. Snorm point, right, assign norm position, whatever. So that's just going to be S. It's the inverse of this. So it's take 100. Right. So there's our snorm. Now we can work out our Morton point, which we can display. So you want 3 floats of 0.2f, right? Yeah. It's cool. So let's give that a go. It should be enough information. I think I got a big enough terminal buffer. What am I seeing? Right, first of all, this needs to be padded by 4. Cool. Second of all, this is all but there's not a lot of spheres, right? Which is good. But we should be able to work that there a bit better. Why am I seeing minuses? Am I doing this right? Oh, I'm divide this y. Perfect. Right, so now what we kind of want to do is pad these out by about 3s. So you need plus the decimal place. So you're looking at about like about, I think 5. Right, nice and padded. Oof. Yeah, the float point one's weird. You have to put the total number of things rather than when it's before the decimal place. Anyway. Right, so these two, we've got to see are they next to each other to the ones at the bottom. And so they kind of are. Let's have a look. So I don't know though. Let's get this in Vim because I feel like I can traverse this better and just cut things out and blah blah and blah, basically. So let's just look at the data we want to look at. So these are next to each other on the z coordinate, right? Right. So maybe we should be making more use of this space, even if we no, because they'll still be the same. On that coordinate, on the Z coordinate. Yeah, we get to expand these out into bits, really. Make a gist of it. Of this whole data set, let's do it. I think I've still got it in my let's do a paste bin or whatever. Just easier. Appreciate it, sir. Is the logline ID ZYX? I'm not sure what you mean by that exactly. Oh yeah, this thing. No, it's just XYZ. Yeah. But the way the Morton code works, good point. Is it? I forgot. Which is in the low bits and the expand bit. X goes in the yeah. So it's X is in the low. So it goes from right to left. It goes X Y Z. Sorry, ZX. ZYX. I think just the way that looks. And the way that looks, at least. Think about it. So I wonder if there's anything that's. Let's go back to Vim with the proper data set. No, I wasn't using hprintf because it's all generated CPU side, all the data at the moment. But in the future, we'll move it to GPU, right? It's just not good. Yeah. Right, let's see if I can decode this. So, we're applying the Morton curve. What is a 9? Ourselves, right? So a 9. Just get the bits out. Oh, I just forget these things. Right, so 9 is 1001. So we've got 2 of those, and a 3 is 11. You've got 2 of those guys. So they're sort of interleaved with each other, right? So the first section is 111. That gives you 7. The next section is. So X is in the middle? Because it's got. Oh no, isn't it? It's the end. Yeah. So it gets you. Excellent. So that's on the 2-bit. Yeah. So it goes X, Y, Z. Yeah. X, Y, Z, X, Y, Z. So I think let's just write out these bits. Just trying to understand this data, And why are they just so different? Or so close to each other, even though... Wait a minute. Yeah, so they're next to each other on the Z. Um, but the X is in the highest. Right. But the X is way bigger. Okay. Right. Hmm. Right, so if the X's are the same, is that right? No, what was I thinking? Alright, let's see the full bit of data now. Yeah, so the X is what gives it the most sort of like so in the way we've done it, the X coordinate is what gives it the biggest sort of defining thing where it could be sort of like at the beginning or the end of the array. Yeah, that's the X coordinate. Which is kind of like what our data is. If we run, let's get rid of the. Right, this is leading me to think actually. Oh, I can't compile that, this thing's saved. Doing it cell by cell. Yeah, but the furthest left goes to the beginning of the array, right? And the furthest right goes to the end of the array. But why are they next to each other in 3D space? They're next to each other on the Z coordinate, but not the X, right? And we've verified this here, right? We've got 16 on the X, right? So, what is wrong? Yeah, something fills up. They shouldn't be next to each other. Go furthest left down the tree. Damn it. We're here. Right, and literally like right next door. There. So, and looking at the data that comes out from the sorted data, something's definitely fishy for that. Like they're close to each other on the Z, according to the data, but they're massive amounts apart. Along the x-axis. Only one apart on the Z there. And only one apart on the Z here, but they're both the same. Right, so is that our data that we're looking at? So they're both the same on the X and Y, one different on the Z. Same for these guys down here. Sorry, what do you mean, Mertender? Welcome, welcome, how's it going? Have a good night. Thank you for coming by. Have you just been chilling? But yeah, so these are they just different by a Z? They don't look it right. They look like that's not one unit on the Z, is it? There's like many spheres fit in there, but they're one different along the X here. Then we go all the way down the right. These are one different along the Z and the X, right? But that's not reflective of the data. Bananas. Have we got an odd number of things? I don't think we do. Right, this is interesting. Yeah, something's definitely off with the generation. Okay. Have a look. So have we got an odd number? We did have these things we were printing out here, right? Wait, I have this core debug, core print. Print basic, there it is. Spheres count, beautiful. $207 spheres, which means the last node shouldn't have. The last node just shouldn't have. It should have one sphere in it. Um. So what is this? These are the nodes, right? And these are all the leaf nodes. Could that be our last one there? Right? That's our or our second last or whatever. That's our last and it's kind of invisible for some reason. And then these work all the way to the left, right? These are our leaf nodes that we're looking at. And then somewhere about here you start getting multiple together, right? These are all of our leaf nodes. Oh, that is weird. These are our leaf nodes. Next to each other, they're complete opposite ends, which leads me to believe these are the two that we're looking at, right? The two groups that we're looking at. Oh my days. Did you just see that? So the first two, for some reason, seem to be linking to ones that are on completely different ends. But then if you carry on, they're all on the left. And they seem to go across in this sort of Z curve order. And then they work their way over to the right hand side. And then you're missing some on the end, right? So that right there seems to be an issue. So why is that? Oh. So let's look at our calc bounds. For the BVH. I could have swore this was fine, but clearly not. leaf node index. So we start off on the leaf nodes, we dispatch across. You know the position on the BVH it is now, right? You should just break before it and see what it does. Break before it. What do you mean by breaking? Because we don't have breakpoints in GPU, but yeah, CPU side, we've dumped all this data. Yeah, I'm not sure. But yeah, it seems like maybe we can print some of the stuff out. I'm not sure though. What exactly do? So we're just launching across. Yeah, they've been calculated. Yeah, correct. But welcome, Prince Mania. How's it going? How's it going? So we dispatch, number of leaf nodes, right? Which is spheres count rounded up divided by 2. So you've got, and then each one is going to pick up 2 spheres. Yeah, so you've got 207, right? We'll just divide that by 2 rounded up. That's fine. So we're just launching that many groups to handle all those. Okay. So we got a leaf node index. We calculate the base node index. We've verified this is correct, right? It's the number of BVH nodes, take away 1 divided by 2. Let's run this through the calculator. So we got 207 spheres. Right, good number. There's 104 nodes. So do 104. Take 1. Oh, I feel a bit of rounding down happening. It'd be 51. Right, let's work on this. Let's work on it in smaller scale. So you've got BVH. Well, you need how many leaf nodes? Oh, you got a bit of cold, fair play. No. Well, hopefully you'll find before the holidays, Yeah. Well, was the trip good though? Did you enjoy the trip? Put on more plenty. So you're going over. Yeah, so I think it's the odd number thing which is getting us here. Maybe. If we just put an even number of It still would have messed us up. Right, so the interesting thing is this has given us an odd number of we've got an odd number of spheres and an odd number of leaf nodes. That's the interesting thing from this. So you got sphere. These are on leaf nodes. Let's say. So if you have 3 leaves, you're just getting this type of tree, right? No, you can't get that tree. Not a binary tree. It's this sort of tree. So you get 2 spheres on there, 2 spheres on there, and then like 1 sphere on there, right? So if you have 5. Yeah, so we got how many? Oh, no. We did this. Okay, I put the numbers put into the calculator with the leaf node numbers. It weren't good. We've done this before, right? 5, take 1. Yeah, then it's just divide by 2. And 2 is the base int, so it's 0, 1, 2. So we start from there. That's the problem. We're starting from there. We're not starting from here. Right. So that's the reason why we end up with 1 node on the right-hand side. Crap. Okay, so what we need to do is we need to pad the number of leaf nodes out. And just simply... Right. So we need to make it a properly balanced tree. So we'll just pad in what we're going to do now is we're going to pad in more spheres, which basically are 0. And these guys are going to, 1, remove all odd numbers, and 2, remove odd number of spheres and remove odd number of leaf nodes. Wish there wasn't so many stairs. Oh man, you got to switch your thinking and enjoy some stairs. You know, the stairs are good, man. You gotta wish there's more stairs. Like, I don't know. I find exercising really refreshing. Really, like, keeps me sane. You know. Like, I wish I could do more. Like, I haven't been able to like go for runs because of my knees for a long time, but they're getting much better now. Yeah, stairs are great, man. Like, take like 2 steps and you can work your legs out more. Always like taking stairs everywhere I go. Yeah, so how are we going to solve the odd number of leaf node problem? Right, well, we just need to make sure that our number is direct. We need to round up to the nearest. So we need to divide our number by 2, round it up, then times by 2 again, and that's the number of spheres we actually need, or something like that. Yeah, right. So we divide by 2 and it's an odd number. Don't we just round up to the nearest 4 then? Because if something's round up to the nearest 4, then a multiple of 4 always is divisible by 2 and you end up on an even number, right? So round up to the nearest 4. But yeah, this doesn't really scale with the tree, does it? Hey, dragon. Leave you drag knee. Welcome. How's it going? You end up over 20 flights. End up with over 20 flights, I think. Awesome. Because we're fitting 2 spheres per. So if we double this number, round it up to the nearest that, and then the division. Yeah, I'm just trying to think of a way we could scale it. But we should probably have a constant somewhere. Right, let's just solve the problem and then we can always just make it better later. So we're just gonna round this number up, basically. So you're saying like padded spheres count equals so I've got this thing called E32, or round up to multiple Have I not got one of these, man? Come on. They exist. Oh, they're only for damn floats. Have I only got these functions for floats? Right, let's just do this guy. Run up to the nearest 4. And then we'll go over from spheres count to padded spheres. So, yeah. And then we can basically just like push. Push on new sphere. And what we want it to be is basically one that's impossible to reach. But then again, or do you want it to be a repeat of the last one? I think. Yeah, last sphere. Then you just say dref s equal dref last s. Because that way all the boxes, you won't create boxes that are like off into oblivion and make a bounding box around it. And you start pairing them up. So I think that's what you want to do, is pad them out, and then your spheres count is just equal to padded spheres count. And that way we shouldn't have any odd numbers, and we shouldn't have spheres and leaf nodes. And that should fix the problem. Right, if the stream dies, I'll be back, but it shouldn't die. Yeah, man. The stream died, so I had to choose the music again, so I put plenty on. Yeah, they're pretty good. Right, hopefully it doesn't die. Right, we're running. Yes. Okay, so we check the... Damn it. Right, let's just go to the furthest left. Goes to the furthest right. We got 207 still on the spheres count. Huh? What? Right, let's put some breakpoints in here. Yeah, I thought that was an F. Huh? Huh? Didn't it compile? I put in the damn wrong... No, I didn't. In the right one. Oh, no, it is in the wrong one. It's in the wrong spheres generator. Dead coder. Dead code. Right, let's run this in the... no. I'm feeling lucky. Let's go. 208. Oh yeah. Right. Oh, these are still overlapping. Really bad. Okay, they're there. Furthest right. Still here. What is going on? So if you look at these two leaves... Where's the leaf? There we go. Oh, we got 3 and 1. You bugger. 3 and 1? In it. No, that's not a leaf then. That's 4. So is there a child on that one? Yeah, there's a child. Good. The left child is the one at the far right? That doesn't make any sense. Oh, no, sorry, it might make sense. Sorry, excuse me there, that was wrong. That's fine, that's fine. So I'm going to go to like the other one that's next to it. Is that a sibling? It is a sibling, isn't it? Yeah, these are siblings. No, they're not siblings. They're not siblings, but they're next to each other in... Ah. Power of 2. We need to actually round up to nearest power of 2 because it's binary tree. The problem is not evenness, it's power of 2-ness. That's the problem. Power of 2 leaf nodes. That's what we need. We actually need to pad a bit more. It's fine. But the problem is you'll be checking extra spheres if you do repeats. And power of 2 spheres is probably quite bad. Like, okay, let's solve the problem doing this way, but let's see if there's a way to solve it better in the future. Power of 2 spheres. Like, I think we've got to... I think basically what we want to do in this case is we have to know, like, this is technically the first leaf node in terms of like 0, 1, 2, 3, 4. Like, this is the way we've got to solve it, basically. But technically the order should be 3, 4, 2. Right. Technically, so it's how we're assigning our spheres in the shader. That's the problem. The oddness doesn't really matter. Yeah, so I think this is actually a bit of a hack. I don't want to go with this method. We've got to figure out on a way of like saying of basically working this out. Yeah, of making it go 3, 4, then 2. Three plus 2 is 5, right? That's the answer, isn't it? So rather than starting from 2, this calculates our base leaf node index. We also want to figure out what is our base power of 2 thing as well, right? So how do we calculate like a 3? Oh, that 3 is our sort of actual first. How do we calculate that? So if anything is less than that, it's the actual first plus the current one. And then, yeah. Okay, I think we got this. So if we do, this gets us the sort of base index of where to start, whereas we want you do like bit LSB or something like that. Most significant bit. So you only get the nearest power of 2. So if you've got 5 nodes here, your nearest power of 2 is 4. That might just be enough. I think we did that in the to get the depth, isn't it? So we get 0, 1, 2. 1 shift left. 2 is 4, then take 1. Something like that. So you get the depth. You get the depth. The max possible depth. So I think we just call it like GFX BVH depth. That's what we call it. You get the depth. So it says it has a depth of 2. Do 1 shift left of that. That'll give you 4. And then you take away 1 and get you 3. So this is your actual base. Okay. So this is like, so you got these two numbers now. So if a number is less than this, we need to bring it up. So if a number is less than one number, if our leaf node index no, so we're starting from this. Shoot. If we go over, we subtract 3 away from it. Yeah. So if node index is greater than this one, we actually subtract Is that right? You land on 5 and you subtract 3 away from it, and you'll get 2. We'll have to try us on a bigger tree, I think. I think that might be the answer. And then if you're still over that, if you're still over the nodes count, then right now to calculate the actual leaf node index, that'll still be right. That'll stay the same. Just the way we calculate the nodes though. We'll have to put a massive comment by this so remember what it actually does. Right, let's draw a bit of a bigger tree. We want to have instead 3 nodes at the bottom. That's not possible. 4 nodes at the bottom. With... join these boys up. What are we doing now in terms of layers? So we don't just one more. You'll still need one more. Damn it. Is this possible with a binary heap? Is this legit? I think so. Hey, Eternal Divine Fox, how's it going? Welcome, welcome. How you doing? Is this possible with binary heap? I think so. So these be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Oh yeah. So you would... is this possible with binary heap? Yes it is, because you just keep filling and then you fill from the left again. Yeah, that's the way it works. Okay. So technically it's possible with less as well. This is good. Okay, BRB, sure. So what we're trying to figure out, we've got this algorithm now, we get the depth, right? So it's 10. What's 11? Nearest one power of, is 8. But it's in log 2 form, so that's 3. So one shift left 3, right? So it's 0, 1, 2, 3. One shift left 3 gets you 8. Then we take away 1, gets you 7. So that's our start, okay? So we do that. So, we start off, we have this leaf node index where it goes from 0 to 0, 1, 2, 3, 4, 5. 5 is at the maximum. It would actually go all the way up to 32, but we stop that. So we say, okay, that number plus the base of 7. So we'll go 7, we'll start first, 8. So the spheres will actually be assigned like this in order, right? 7 will go first, 8 will go second, 9, 10. Right? You get to 11, and it's like, a bit too big. So we take away 7. Is that too much? So 11 take away 7 gets you 5. Right? Right? Is that right? What does it get you? Did we do this right? Not 5, is it? It's 3. Oh, it's 6, isn't it? Are we off by 1 now? It might not work. Yeah, why are we off? Why is it different? Damn it. So, it's actually just gonna get a 6. So that's not the number that we... we want. Yeah, taking away this isn't enough. It really isn't enough. Right, so it's actually a little bit different, which is fine. We've got different examples now to work with. So what number do we need to take away? We're on 11. Right, how do we... Well, you just take away the difference between these two, isn't it? Is that right? Yeah, it's just a wrapping thing, isn't it? You need to take away whatever the difference is between 11 and 5. So we can get that number. It's quite easy. It's here. So it's this number. I'm going to call it TTT because I'm being lazy right now. But you essentially want to go, like, this number's going to be smaller. So it's... You're wrapping it back round to there. So it's bigger, take away the smaller, right? And then that's the difference that you're going to subtract this by. Ooh. Thank you. Rasmusko. Thank you, appreciate it. Spreading the word of Rust on stream. Legal. I'm joking. Thank you. Appreciate the effort you put into this. So yeah. So drag and drop that into here. Oh, look at this guy. Pretty cool. Whoa. Trying to figure out what I'm looking at. There's the Z curve, look at it go. Yeah, so it should make its way across the x-axis. Yeah, this is the problem we're trying to deal with now. This is excellent. Yeah, I'm glad we found the problem, but this is also very cool. Because this is what we basically want. It should go across like that. Because then we'd actually get a nice BVH split. Literally 50-50-ish. It will overlap a bit, but it won't be one inside the other like it currently is. It's very bad right now. But yeah, I think we should be able to see this in literally just a minute. Just got to finish this bit off. So we're getting the old one, which was wait, where's our? That was Milton, wasn't it? Yeah, so we've got 5. Yes, we've got 11. Yes, so we've got the number 5 here. This is 5. And then you're like 11. As an example. So you're saying 11 take 5. Gotta get you 6. Right. So what you're saying is when you reach 11, take away 6. And you'll like then go from 5 basically, right? And then 6 take away 12 take away 6 equals 6. And then but the problem is this end node is not working anymore. Because that would have wrapped back around again. So what you're saying is if this is equal when after you take it away, if this is equal to, this is so confusing, this code. Literally, someone read this and be like, what is this person doing? This guy's a genius, but not really. So I probably need to literally describe it in some, you know, so that people can try and visualize it. Yeah, so you want to say something like node index is greater than, if that's greater than or equal to this variable here. We've got to name these better. Right, that'll be it. Let's just double check. So you're getting this. This guy, which is, 7. We know that's going to be 7, that's fine. Plus that node, if that's greater than the nodes. Yep. 11 take 5, yep. 6. Yep. Yep. Alright, that ought to be good enough, I reckon. We take that for a spin. Right, the GPU could crash. If it does, I'll be. What's this? Make sure we compiled it. And away we go. Right, it didn't crash. But we've definitely gone and buggered something up. I thought, do we use leaf node index or node index for anything else now? No, node index is fine. I know that for sure. Well, leaf node index. Do you use that for anything else? Oh, in our sphere ray tracer, we need to use the same maths. Crap. In our sphere ray tracer, we need to know where the base. We need to basically remap it properly as well. Damn it. So you effectively just want to remap what we remapping. Yeah, so we're sort of going from a node index now to a. So we need to somehow go from like a node back into the array of spheres again. Like we could store an index in there and make it easier, but it should be able to reverse that back. You bugger. So you've got a node index, so we need to go back into the array. So this should just take away the base one, which was say 5, but that starts from here. That's not right. We need to actually start from over here and then spill over into the 5. Right, go the way over and spill over into the 5. So give your node index, take away the base, then if you go over, take away that difference number. There's a difference number we need to calculate. That's here. We'll bring these stupid variable names back in, right? But the idea is you need to take away this new sort of like base 1, which we do. And then we say if you go over, which will just delete the if statement. So if this leaf node index goes over, then we need to take away a difference. No, this feels wrong. Yeah, if it goes over, we take away... No, but it would be negative, wouldn't it? Because you would have done... It would be negative, which means if it's signed, you need to add whatever this number... Yeah, whatever that diff number is, you need to add it. So we go back into signed numbers instead. And we'll do... So if that is less than 0, then we need to add that difference, which would be... We've got bounds checking, so it shouldn't crash. Right, so you can still work out those sort of variables there, right? And that'll be... So let's just look at this, right? So you're saying if you know, 8 minus 7... Oh, sorry, wait. Yeah, 8 minus 7, that'd be 1, right? So that's fine. But when you start going over here and you get to 11, it'd be like 11 minus 7. And that'd actually be 5. So then you do... No, it won't. Sorry, you won't be in 11. Sorry, you'd be saying 5 take away 7. That'd be minus 2. So what you need to do is you need to add that difference you had from 11 to that, which was 6. So you add 6. 1, 2, 3, 4, 5, 6. It lands you there. And you're into the array, basically. So it'll get you minus 2 plus 6, which would be 4. And then you can use index of 4 to then look at your base. You times that by 2, there's your sphere index. And then you go over those two spheres. Right, this seems sensible. Just gotta make sure. Right. We're missing the top and sides, damn it. But things are looking better already. That's good. How are we missing the top and sides? What have we done? Right, we're getting nodes there, just the spheres are not there. These are probably our dangling nodes. But I'm not sure what the perf is, to be honest. Are we dumping this every frame? Of course we are. See, the performance is already better because it was about 1.2 ms. Right, so it's already an improvement. We still make it a bit better though. Sorry, we're just missing data here though, so we can't really... But yeah, that's already an improvement doing it that way at least. But why didn't it work? That is the question. What are we doing this wrong? Like, this went into the negatives. What is that? Yeah, this is a problem, innit? This is saying, hey, if RB, yes, that will get rid of the 5. That ain't good. So what we actually want to do is bring this out here. And you probably want to run some maths. And then just be like, if this is greater than or equal to 0. That'd be what we want. And away we go. Look at that. Please don't say that's slower. Is that actually slower than what it was? I'm confused. We got a BVH and now it's sort of surely subdividing better. Still a little bit confused, not gonna lie. We're also not able to view the whole BVH here. Huh. Also can get some funny business here. What is that? Right, let's quickly just undo this. We're gonna post a GIF for the link. I'm not sure what you mean. What, so you can share a GIF? You can share links, that's fine, in the chat. Or just post it on the Discord, if you want me to see it. Right, so if we undid this, right, all this beautiful work that we've done, just to see the performance. That's about 1.18 ms. We're clearly rendering everything, I think. But then, well, I don't know. Yeah, we're able to scan through and see everything there except for the end. But for some reason we put everything back. And the performance is worse, even though the BVH appears to be better. Like, I don't know, we've got to check the quality of it actually, to be honest. Right, it starts doing 2s from here and it just goes from one side. Oh no. No, it's still problematic. I think the number is a little bit off still. It's wrapping round. Yes, something's up with the... Is it still starting from the... Yeah, something's definitely fishy. We'll figure that one out. Damn it. Right, so we've got about like 1.2, 1.1 ms to beat. Basically when we reorder this, and it's still a little bit off. But we're definitely getting there. Yeah, you see outside the box, isn't it? The BVH tracer viewer thing, that just looks at the boxes. It doesn't know anything about the spheres. So that's not gonna have to change either. What is this? Oh yeah, you're plotting it. Yeah, I'm confused as well. It doesn't seem right. I don't know. Yeah. No, it doesn't look right, does it? Yeah, but it works out fine here. Wee, it's pretty cool. Um, um, right, so this will get you the 5, right? It's 11 minus 1 divided by 2, 5, yeah? Then 11 take. We should try it out on this. We didn't try it on this, right? So we did. It makes sense though. Yeah, so this gets you the 3. We know that it gets you the 3. This gets you the... this gets you the 2, right? Because it's 5 take 1 divided by 2. Yep. This gets you difference, so it's 5 take away 2 gets you 3, right? So it means when you have 5 and onwards, you can take away. And it should just wrap around. Right, it could be something to do with this code then. So if we got a 5 in this case. No, you never get 5, sorry. If we get a 2, you say 2 take away 3, that'll get you minus 1. You say, well, if you're less than 0, add 3. So we add 3 to minus... Wait. You add 3 to minus 1, which gets you 2. So that's 0, 1, 2. And then that makes sense. Are we doing anything with this still? No. Seems pretty sensible to me. Yeah, it's very weird, definitely. Um, right, let's double check this one again. So you've got 5. Uh, no, that'd be 7, isn't it? Yeah, it's 7. Uh, yes, you're saying 7 plus 5, that lands you on 11. And because you're at 11 or greater than or equal to 11, we calculate that difference again. So you take away 6. Right. And then you just work from there. Yeah, it seems fine to me. I'm not sure what the issue is. There's definitely... still something very strange going on. outside the box. See, we're still getting this sort of empty guy as well, which was getting in the previous code. Very confusing. Right, I think I might need to put a pin in it there today because it's getting kind of late. Need to get ready for bed and go to work tomorrow and all that jazz. But good session. We found out we found out that ideally we should be able to get them to order nicely enough so the BVH should be in a better quality than it is. But we've been trying to fix it and somehow made it slower again. I don't know how. But we should, when we improve the quality, it should be better. But there's some definite issues with this. Like, it shouldn't wrap here. It should go from one side to the other. Wait, where is it? When it's a bunch of twos there. It should go from like left to right or right to left, but it just wraps. And that's not a good sign. But yeah, when we get that behavior, it should be 20% better, which is good improvement. Okay, so let's find someone to raid. What's Mike doing? Nah. He was streaming for a while. Let's raid Nico. Right, good to see everyone. I'll see you all on Sunday. I'll stream at 6 p.m. GMT. Have a good one. And I'll see you there. Catch you later. Thank you for coming. Bye-bye. Bye-bye.